In this video, we're going to examine another problem involving friction. In this problem, we have two blocks that are stacked upon top of each other, and they are both placed upon an inclined surface. And the inclined surface is at an angle of theta. So we have block 1, which is in green, block 2 in purple, and we have an angle theta that this block is at. We're told that the coefficient of friction between the blocks, so here at this interface here between the blocks, is mu f1, and we're told that this is equal to 0.6, and between the second block and the inclined surface itself, so here we have a coefficient of friction UF2, which we're told is equal to 0.25. So the roughness between the two blocks is much rougher than the roughness between the inclined plane and block 2. Finally, we're also told that the angle theta is equal to 20 degrees. The weights of the blocks are given, so we have W1 is 30 kilonewtons and W2 is 20 kilonewtons, and we're asked simply what happens to the blocks. So we say simply, we need to find out. So we have to think through what could happen with these blocks. And we have a couple of scenarios that we can imagine. And the simplest scenario is that nothing happens to the blocks. There are no applied forces on this system. It's completely imaginable that the blocks just stop where they are. Okay, we have another, and that is this scenario 3 that I've mentioned, that they could just stop where they are. We have a scenario where just block 1 slides. So block 1 slides on its own, block 2 remains in place, and we get a relative motion along the interface between the two blocks. And then the other scenario we have is that both blocks slide. And if both blocks were to slide together, then we would get motion occurring at this interface here between block 2 and inclined surface. And that would mean that the surface between blocks 1 and 2, there would be no motion, so we wouldn't be generating the full friction possible for that to happen. Okay, so let's find out and draw the free body diagrams for the scenarios that we imagine, and do some calculations and work out what indeed does happen to these blocks. So we're going to first of all look at the scenario where block 1, the top block, slides. Block 2 remains in place, and we're going to draw the free body diagram for that system. So if we imagine we have global coordinate axes of y and x, because we're at an incline, it's quite often, not always, but I prefer to actually have a set of rotated axes compared to the global coordinate system. So we're going to be working with these axes y dash and x dash. So let's write down what we're doing. Scenario 1, block 1, that's the top block, remind ourselves, slides. So we'll draw the free body diagram for this top block. So here's the block. We have our coordinate axes x dash, y dashed, Remind ourselves we're drawing a free body diagram, and so we will have, going from the centroid of the block, we will have the weight W1, and this will be at the angle θ1. We will have the normal force, let's call that N1, so that's between block 2 acting on block 1, and to resist the motion, so remember we're going down in this direction, so in the negative x1 direction. To resist the motion, our friction force needs to point in the positive x dash direction, and we'll call this F1. And let's just remind ourselves of the data that we've been given. So we have W1 equals 30 kilonewtons, mu F1 equals 0.6, and theta equals 20 degrees. You might need to calculate this in radians in your calculator, or if you're using MATLAB or Excel, be careful of what your calculator uses, whether it uses radians or degrees. Anyway, let's take the sum of the forces in the y dash direction first of all. So sum of the forces in the y dash direction, so we have pointing downwards, so minus W1 times the cos of the angle theta plus N1 pointing upwards in this y dash direction must be equal to 0. So we'll rearrange the equation and insert the known quantities. So we have N1 equals 30 multiplied by the cos of 20 degrees, and therefore N1 equals N1 equals 28.2 kilonewtons. We're going to use this result later, so we'll double underline it. Now we'll take some of the forces in the x dash direction. So let's remind ourselves the free body diagram. So we have F1 pointing in the positive x dash direction and a component of W1 in the negative x dash direction. So that is F1 in the positive x dash direction minus now the sine, minus now W1 multiplied by the sine of this angle theta, and to be in equilibrium must be equal to 0, and therefore rearranging this F1 and inserting the known values for W1 and the sine of theta, we get that F1 equals 10.26 kilonewtons. And finally, for this scenario, let's go back to our free body diagram. We know with our dry friction model that we can calculate our maximum friction possible from the dry friction model. Let's remind ourselves that Fs was equal to mu n. This was the general formula. Now let's write that specific to this situation. So F max, let's call this 1 because we've got another scenario to consider, would be equal to mu F1 multiplied by the n that we just calculated. So that was equal to the value given, 0.6, multiplied by the value N1 that we calculated. So that was 28.2 kilonewtons. and calculating that value now, we get that F max 1 is 16.9 kilonewtons. And so at this point we can see that we've calculated that the friction value between the two blocks must have been 10.26 kilonewtons, but the maximum value of the friction is 16.9 kilonewtons. And reminding ourselves of this dry friction model, so we had F on this axis, went up and up and up, then dropped until we got to the kinematic friction level. Our S value here is calculated at 16.9, but we've only managed to get ourselves up to a value here of 10.26. So we're at a point where we haven't quite reached this maximum friction level, and therefore we're not sliding. And so we can, therefore, block 1 is not sliding. So when we looked at the problem, let's scroll back up right to the original problem. So we have blocks 1, blocks 2, take this away now. We also said it's completely possible, so this is scenario number 2, that both of these blocks will slide down the incline together. So we need to analyze this and draw free body diagrams. So let's write down what the scenario 2 looks like. Scenario 2, both blocks slide. And let's draw ourselves a free body diagram of the bottom block, so block 2. So FBD of block 2. So here's our block, and I need a bit more space, so I'll just remove those words for a second. In this case, for block number 2, I'm going to cheat a little bit in terms of saving space. I have W2, and this is again going to be at that angle theta. I'm expecting a normal force N2 to come from the incline to stop the motion along the incline. I'm expecting a friction force F2, but now the free body diagram gets a little more complicated in this scenario. So we also have the weight of block 1, and as a result of the weight of block 1, we will have a normal force between block 1 and block 2. So block 2 would be creating a normal force pushing on block 1, and block 1 would create the equal and opposite force acting on block 2. So the N1 we calculated is now acting on block number 2. Finally now, we have a friction force keeping block 1 and block 2 kind of glued together. And let's go back up. So block 1, to keep block 1 from sliding past block 2, so moving like this, we need to have a friction force opposing that motion, and that is what we did in analysing the free body diagram of block 1. However, on block 2, what this means is the equal and opposite force is coming from block 1 and pushing on block 2. It's kind of complicated. I've spent some time to think that through, but there are equal and opposite forces acting here. So the weight of block 1 finds itself on block 2 in two ways. One, from the normal force N1, and secondly, from the friction force generated between the two blocks that gives us F1. And before we go on to do the calculations, let's just remind ourselves that we're told that W2 was equal to 20 kilonewtons and mu F2 was equal to 0.25, and we have values of F1 and N1. So we have F1 equals 10.26, even, and N1 was 28.2. And both of these are in the units of kilonewtons. So a more complicated free body diagram, but now we've broken it down into all of these components. We can go about writing some of the forces in the directions, and again we are in these rotated coordinate axes S dash and Y dash. So let's write down, let's try and keep that on the screen if we can, the sum of the forces in the Y dash direction. So we have, pointing upwards, we have N2, but we have pointing downwards, so minus N1, and we have a component of W2 pointing downwards, so minus for pointing down, W2, and a cos of theta to get the component of W2. And for equilibrium, so just at the point of impending motion, if that's the scenario, must be just about equal to 0. So we're going to rearrange this slightly, and we want to know N2, so we'll rearrange in terms of N2. So we have N2 equals 28.2 plus 20 times the cos of 20 degrees. And we can put that straight into the calculator. Everything's known there now. And we get 47 kilonewtons. 46.98. But rounded up to 47. Okay, now we'll have a look at the sum of the forces in the x dash direction. So sum of the forces in the x dash direction. So let's remind ourselves of free body diagram. So we have F2 as the only force moving in the positive x dash direction, and we have F1 in the negative x dash direction and a component of W2 in the negative x dash direction as well. So let's write that down. So we have F2 minus F1 minus the W2, and now multiplied by the sine of theta, must be equal to 0, and we can now calculate a value for F2. So this is equal to 10.26, the value of F1 we calculated, plus 20 times the sine of 20 degrees, and we get that F2 equals 17.1 kilonewtons. And let's just remind ourselves that this 10.26 that we calculated was not equal to mu1 n1. because we weren't at the limiting friction case. Okay, so now we have a value for what F2 is. What we need to now calculate is what is the maximum friction that we could possibly generate along this surface. So along here, what is the limiting friction value F max 2? So F max 2 is equal to our friction coefficient mu F2 multiplied by the normal force N2, and that is equal to 0.25 times by the 47 kilonewtons, and that is equal to 11.75 kilonewtons. And so we can look at these two values. The friction force needed at impending motion would be 11.75 kilonewtons. However, we've calculated that the force between the two, with the weights involved and the friction coefficients involved, would be at a value of 17.1 kilonewtons. And therefore, because F2 is greater than F max 2, we know that block 2 must slide. So by developing the different scenarios, we finally got to the point where actually the original block must be sliding. There is no way that it can be in equilibrium, and both, because of the friction generated between the two blocks, that both blocks are sliding simultaneously.